This is the final section and it's about regions in the complex plane. Let z0 be a complex number and epsilon be a positive real number. Now we are going to define a set of complex numbers called the epsilon neighborhood. In short, we would write like this, NBD, okay, because it's a bit cumbersome to keep writing neighborhood like this every time. So we would write NBD. An epsilon neighborhood, or more specifically the epsilon neighborhood centered at that complex number z0 and having radius epsilon, is this set. It's the set of all complex numbers z whose distance from that z0 is less than epsilon. So that means if you locate the point z0 in the complex plane and consider the circle centered at z0 whose radius is epsilon, then this is the set of all points which lie in the interior of the circle. So that is your epsilon neighborhood centered at z0 and having radius epsilon. We can just sometimes simply say that it's an epsilon neighborhood if it's understood what the center is. Associated with an epsilon neighborhood like this, we have this other set, which is almost just like this one. The only difference is that now you have this extra condition that the distance between z and z0 has to be greater than 0. You can see one thing immediately from the definition of epsilon neighborhood centered at z0, that the point z0 itself is inside this set. However, in this set, which is different from this one, that point is not there. Okay, so it's called the deleted neighborhood centered at z0 with radius epsilon. And it has another name also. Sometimes we call it a punctured disk. It has been punctured here at the center. The central point is not there. Now next, let S be a subset of C, a set of complex numbers, a set in the complex plane, and let z0 be a complex number. We are going to call z0 an interior point of that set S. We call z0 an interior point of S if there exists a positive real number epsilon such that this epsilon neighborhood centered at z0 is entirely contained inside S. Let's see how it looks in a figure. Say this is your S. Let me be more clear. This is your S means what? By that I mean that S is the set of all points that lie in the interior of this irregular region, and along with that, the points that lie on this closed curve are also points in S. Okay. Now inside this S, not on the closed curve, but in the interior of this S, say you have a point z0, which is a complex number. Oh, and do not forget that all these things are happening in the complex plane. Then this point is an interior point of this S because there exists some small enough epsilon for which, if we consider the neighborhood, epsilon neighborhood centered at z0, that is entirely contained inside S. That is why z0 is an interior point of this S. However, just below that you see this other S, which is a line segment in the complex plane. That is also a legitimate set. And then you locate some point in that line segment, on that line segment. This is not an interior point of this S, although it's a point in S, but no matter how small an epsilon you think of and consider the corresponding epsilon neighborhood centered at z0, this is never going to entirely lie within this line. So that's why this z0 is not an interior point of this set S. Now we will also call z0, not that z0, something else, an arbitrary point again, an exterior point of the set S, if this time there exists a positive epsilon such that the epsilon neighborhood centered at z0 does not intersect the set S. In case of interior point, it was lying entirely inside S. This is the other extreme, where it does not have anything to do with S. It does not even touch S. Say if our S is that S, and this time we consider this point, which you clearly see kind of lie outside S, but inside outside we use these terms vaguely. Now only we are doing something that will allow us to use inside and outside rigorously mathematically, and you can understand what we are going to call the inside of a set and what we will call an outside. But anyway, so say this is your point Z0. Okay, this is an exterior point of this S because there exists an epsilon neighborhood centered at Z0 which does not intersect S, it's disjoint with S. And finally, we call Z0 a boundary point of S if it is neither an interior point of S nor an exterior point of S. For example, this point on the curve. Why is this point not an interior point? For it to be an interior point, there should be an epsilon neighborhood with that point as the center which lies entirely inside S. That is not possible. Because of the location of the point, it does not matter how small an epsilon you choose, some part of this neighborhood is going to lie outside. So that's why it's not an interior point. But it's also not an exterior point because you won't be able to find such a neighborhood centered at that point which does not intersect S. Again, no matter how small an epsilon you choose, how small the neighborhood you choose, some part is going to intersect S. So that's why it's neither an interior point nor an exterior point. It's a boundary point by this definition, and it makes sense also. Everything makes sense, everything looks so natural. Interior point, exterior point, boundary point. The set of all interior points of a set S is called the interior of the set. The set of all exterior points of S is called the exterior of S, and the set of all boundary points of S is called the boundary of S. Without being too rigorous, in this figure you can understand what the interior, exterior and boundary are of S. The interior is the region which lies, which is enclosed within this closed curve. The exterior is the outside, and the boundary is that curve itself. There is one more very easy observation which nevertheless will be useful. An interior point of a set is an element, a point in the set. An exterior point of a set is not a point in the set, it lies outside the set. However, a boundary point sometimes is a point in the set, sometimes it may be a point in the set, it may not be a point in the set. All these things, all these remarks can be understood and can be seen more clearly when we consider a concrete example and not a schematic diagram like this. This is one concrete example. The unit circle centered at the origin is the boundary of both these sets. Let's see again in a diagram, but this time it's more concrete. Say this is your unit circle. Here I messed up a little, you know how bad my freehand drawing is. But anyway, you get the point. So this is the unit circle, which is the circle centered at the origin and having radius 1. So it is this. What does it mean? What exactly are we calling the unit circle? We are calling the set of all points which form this closed curve the unit circle. Alright. What is this set? This set is what lies inside the circle. Say this is your S. Okay. Now looking at what we did here just now, you convince yourself that for this S, every point that lies inside S is an interior point. All the points that lie outside this circle are exterior points of this S, and all the points that lie on the circle are boundary points of S. So that is why the circle which is the set of all boundary points of S, is the boundary of this set S. Similarly, what is this set? This set is that previous S, but along with that we have the circle also. For this set also, the boundary is the circle itself. So here you can see what I said just now. For this set, no boundary point is in the set, but for this set, all the boundary points are inside the set. So sometimes boundary points are there, sometimes they are not there. Also, it's not uniform like what you see here. In this case, no boundary point is in the set. In this case, all boundary points are in the set. But sometimes we have situations where, say, some boundary points are in the set, some are not. We will see what these things ultimately lead to right now itself. A set S is called open if it contains none of its boundary points. Now we have come to the main thing, open sets, closed sets. This definition of a set being open may be slightly different from what you have got elsewhere, but the other definition that you have got somewhere else, which involves interior points, is equivalent to this one. But anyway, let's see what this means. What this definition is saying is that, say you have a set S, then it has some boundary points, okay. If it contains, whether it has or does not have boundary points, that's not the point here. Whatever boundary points it has, none of them is inside the set S. If that's the case, then we will call S an open set, like this one. This set has boundary points, and in fact, those boundary points form this unit circle. However, none of them is inside this set. So that is why this set is, by this definition, an open set. So a set is open if and only if all its points are interior points. And this condition, that all the points of a set are interior points, is actually the other definition of an open set, which may be familiar to you. So this line says that these two definitions are equivalent. You can use either one of them. And it's also not very difficult to see why this statement is true. Remember what I said, moments ago, that a point which is an interior point is inside the set. An exterior point is outside the set, always. However, boundary points sometimes are inside the set, sometimes they are outside. Alright. Suppose that a set is open according to this definition. Then it has none of its boundary points. So then how do you conclude that all its points are interior points? Okay, you think of the set, some set in the complex plane, okay. And you pick a point from the set. You want to conclude that it's an interior point. Can it be an exterior point? No, because exterior points always lie outside. So that means because every point with respect to a set is either an interior point or an exterior point or a boundary point, and exterior point is ruled out, so your chosen point is either an interior point or a boundary point. But by the definition of openness, it cannot be a boundary point. So you are left with only one option. It has to be an interior point. That is why if the set is open according to this definition, then all the points inside the set are interior points. And I want you to think why the converse is also true. Okay, so you do that yourself. And this is the related notion. A set S is called closed if it contains all of its boundary points. In case of an open set, no boundary point is inside the set. In case of a closed set, all boundary points have to be inside the set. For example, this one. Just now we saw that for this set also, just like this one, the unit circle is the boundary. But unlike this one, this set has all of its boundary points as points inside of it. So that is why this set is closed. and this one is open. Do you see how nice these definitions are, which are slightly different from the usual definitions of open and closed sets? Nice in the sense that they are related directly as definitions themselves. An open set is a set which has none of its boundary points. A closed set is a set which has all of its boundary points. Now, after the definition of a closed set, we naturally have the definition of the closure of a set. The closure of S is defined as the set S together with all its boundary points. For example, the closure of this open set is this one, this closed disk. Why? That's because just now we saw that the boundary points of this open set form that circle, right? The unit circle, and that is included in this. So in this we have this as a subset along with that circle. So that is why by definition it is the closure of this set. It's a fact, it's an extra fact that the closure of any set is itself a closed set. You think why? I am not going to elaborate on this. Okay, these are well-known results from topology and analysis, real analysis in fact. So we are going to go ahead. There are some sets in the complex plane which are neither open nor closed. The reason is the definition of open and closed sets involving boundary points. You see, open sets are sets which contain none of their boundary points. Closed sets are sets which contain all of their boundary points. So between these two extremes, there obviously will be intermediate states. For example, this punctured disk is neither open nor closed. This one is obtained from this set by removing the origin. Okay, so you have to imagine that here. It's a bit difficult to show. I mean, you cannot of course show removing the origin. You imagine what this set is. It consists of all the points which lie on the circle and inside the circle, but the origin is not included. Okay. And the claim is that it is not open and also it's not closed. Why is this not closed? For a set to be closed, what is the definition? That all the boundary points have to be inside the set. For this set, almost all the boundary points are inside the set, most of which are lying here on this circle. They are boundary points. But there is one boundary point which is not included in the set, which is the origin. How so? Why is the origin a boundary point of this set? The origin, of course, is not an interior point. That we can immediately say. Why? Because recall that an interior point has to, after all, be a point inside the set. This is not included. So interior point is ruled out. Can it be an exterior point? No. Because if you think of an epsilon neighborhood of the origin, which is basically what? The interior of a circle whose center is the origin. Can any such epsilon neighborhood lie entirely outside this so that it does not intersect this set at all? No. It will intersect the set at infinitely many points. The origin itself is not included, but its neighborhood is included, right? Some region, no matter how small, around the origin you choose, that region will have infinitely many points of this set. So that is why this becomes not an exterior point either. It's neither an interior point nor an exterior point. So it's a boundary point, but it's not included inside the set. So that is why the set fails to contain this boundary point. So that's why it's not closed. But the set is not open either because it contains some of its boundary points. In fact, most of them are inside the set, which are the points on this circle. So that's why it's neither open nor closed. And then we have this very peculiar situation. The set of all complex numbers is also a legitimate subset of itself, and as a subset of itself, it is both open as well as closed. Let's see why. Say I use a notation to denote the boundary of this set, del C. You need not worry too much about this notation, okay, it's not used in this book, I am just simply writing it from elsewhere. If you want, you can just write set B, okay, say B is the boundary of C. Then it is empty because there is no boundary point of C. Every point is an interior point of C. If the set itself is the entire C, then every point is an interior point, so there is no boundary point. Okay, what does this mean? It means two things simultaneously. Because this is the empty set, so it's contained in C. Empty set is a subset of every set. So technically, every boundary point, there is no boundary point, but still the boundary is entirely contained inside C. So by definition, C is closed. But at the same time, the boundary does not intersect C also. Okay, it sounds counterintuitive, but because there is no boundary, so the boundary is simultaneously inside C as well as it does not intersect C. So because of this, C is closed, and because of this, C is also simultaneously open. Then we have the notion of a connected set. A set S is called connected if whenever you choose any 2 points in S, say Z1 and Z2, then they can be joined by a polygonal line which lies entirely in S, and a polygonal line consists of a finite number of line segments joined end to end. Let's try to understand what this means. Say your S is this very ugly looking region, which is an irregular region, somewhat elongated, and it's actually what is it? It is the region enclosed within this simple closed curve, which looks very wavy and crooked, but anyway it is some region. Then this condition says that, say you choose these 2 points Z1 and Z2 inside S. This condition demands that there be a polygonal line joining these 2 points which lies entirely inside S. And a polygonal line by definition consists of finitely many line segments joined end to end. If this happens for any pair of points in S, then we call S connected. Let me also give you an example. Example means a schematic diagram of a set which is not connected. Say your set is the union of these 2 regions, then this is not connected. That's because if you say choose a point from here in one of the 2 parts and the other point you choose here, then you cannot think of a polygonal line that will take you from Z1 to Z2, but at the same time all the while being inside S. No. If you want to do that, you have to leave your set S somewhere in some way. So this is not connected. Now let's see one example, a concrete example of a connected set. This annular region, the annulus, is connected. It is this region in the complex plane which lie between these 2 concentric circles, both having the origin as their centers. One of them has this radius 1 and the other one has radius 2. It's the set of the points which lie between these 2 circles. It is connected because that condition turns out to be true. No matter which pair of points you choose in this region, there will be a polygonal line which will link them and which will also lie entirely inside this region. And then we have this other definition. An open set that is also connected is called a domain. Here this word domain in complex analysis has a specific meaning. It's not exactly that domain that you find in function theory, that is the domain of a function. It's different. A domain in the complex plane is an open set that is also connected. This, for example, is a domain because it's connected as well as open. You can verify that this is open. Can you guess what the boundary points of this set are? The boundary points form these 2 circles. none of them is inside the set. So that is why it is open and connected as well. So that's why it's an example of a domain. And a domain together with some, none or all of its boundary points is called a region. That means a region itself need not be a domain because it's allowed to contain boundary points, whereas a domain by definition cannot contain any boundary point because it has to be open. Say you have a domain and then you decide to also include some boundary points along with the domain. So that changes the set. Such sets are called regions. Domains are regions, but every region is not a domain. Next we have bounded sets. A set S is called bounded if all of its points lie in the interior of some circle where R is some positive real number for a large enough R. But if no such circle exists which can capture all the points of the given set S, then S is called unbounded. So this set, some set in the complex plane is bounded because there is a large enough circle to contain it fully, whereas this half plane is not bounded. What is this half plane? It's the set of those real numbers whose real parts are non-negative. So that means this consists of all the points that lie on the imaginary axis as well as to the right of it. Okay, so that half plane. There is no circle, of course, which is large enough to entirely contain that. That is why this is an unbounded set. And finally, we have the definition of an accumulation point. A point Z0, a complex number Z0 is called an accumulation point of the set S if for every positive real number epsilon, this deleted neighborhood, okay, not ordinary epsilon neighborhood, centered at Z0 intersects S. That means this intersection is non-empty. So what does this condition actually tell us? It tells us that no matter what epsilon neighborhood we choose centered at Z0, that epsilon neighborhood is going to have at least one point of the set S which is not Z0 itself because of this deleted condition. So in this sense, Z0 is like a celebrity. In its neighborhood, no matter what neighborhood you choose, there are always fans who are eager to get close. And that is why, if you understand that, this becomes clear. So every accumulation point is either an interior point or a boundary point of the set S. Why? Why can it not be an exterior point? Because it's a celebrity. It will never find a peaceful neighborhood where there is no fan from S. That is why we have this. And that is why if S is closed, if the set is closed, then it contains all of its accumulation points. Let's see how this one follows from the previous line. You take any accumulation point of S, anything, say Z0, okay? Then by this previous line, that point is either an interior point or a boundary point. If Z0 is an interior point, then obviously it's inside S. Okay, so S contains Z0. However, if Z0 is a boundary point, then also it is inside S because S is closed. Okay, so you find this fact that a closed set contains all of its accumulation points. It's a result, it's a fact, it's a consequence. However, the definition of closed set says that a closed set contains all of its boundary points. This term accumulation point, in its place you can also use another term limit point, which I think is more familiar to most of us. And this statement is sometimes taken as a definition of closed sets, that a set is said to be closed if it contains all of its limit points. But before taking that as the definition of closed set, you also have to make sure that the converse of this is true as well, which I argue to prove. Okay, it's not very difficult, you can think of it yourself. And the authors end this section and the chapter also with this final remark. The origin is the only accumulation point of this set, I divided by n, where n varies over the set of all positive integers. So these points you can obviously imagine they are lying on the imaginary axis above the real axis, and as n increases they gradually come down. If you take n equal to 1, you have I, then I divided by 2, I divided by 3, so like that they get closer and closer to the origin, they accumulate near the origin. Now before I end this video, let me give you one important advice, what not to do. Don't memorize these definitions one after another, and especially don't write them down in a notebook and then start memorizing. That's not how you learn. The thing to do is to just leave these things here itself. We go ahead and we see how these things appear in actual situations, theorems, example, whatever we are going to see. And then at that time, if you do not remember any one of these definitions, you go back and see what the definition is. In this way, if you go back and forth, you will also understand as well as remember the things much more naturally. This is why you don't learn a language by memorizing words from a dictionary. You start speaking, you make mistakes and you then rectify yourself. That's how you learn things.